last time, well, we've been talking about homology, and we proved 2 times ago that a short exact sequence of chain complexes induces a long exact sequence in homology right, which came down to constructing a connecting homomorphism and then proving that this was exact. Right? So these maps induce these maps, and then this one we constructed. So applying this to natural short exact sequences in singular homology, well, of singular chain complexes, for example, given a pair, we have the chains in A mapping into the chains in X, mapping into the relative chains. So applying it to this short exact sequence, we get the long exact sequence of a pair all right. Similarly, for reduced homology, right? Reduced homology, we have augmented chain complexes, and they also form a short exact sequence, and so you can also get a long exact sequence. And also for a triple, right? So this means that B is a subspace of A, is a subspace of X. So you have AB includes into XB, and the quotient is XA. Okay, and then we talked about excision. Which is a property of these relative homology groups. And it says that if you're taking the relative homology of X with respect to A, then you don't care what's going on inside A. Right? To the extent that you can remove part of A, and nothing happens. So let's say you have a triple where the closure of Z is contained in the interior of A. Then the relative homology group is the same after you remove C. And so in the makeup lecture, which you may or may not have had time to watch yet, we gave a proof of this. And then as a corollary, we saw that if XA is a good pair, right, which remember means that A has, let's say, is a deformation retract of a neighborhood in X, then the relative homology groups are the reduced homology of the quotient. Okay, so that's where we are. Any questions on this? Yes?
So in the definition of a good pair, it's implicit that it's a pair under the standard definition, yes?
Yes, so A is a subspace of X. Yes. More questions? Okay, so this tells us that for good pairs, the relative homology groups have this nice geometric interpretation. They are the homology groups of some space, and it's a very brutal way of deciding that A doesn't matter. You're just collapsing all of A to a point, right? For an arbitrary pair, something similar is true. In that the homology groups are going to be the homology groups of a space. But the map where you just kill A, collapse A, doesn't behave as well for an arbitrary pair. So instead, we're going to kill A homotopically. So kill A by forming the mapping cylinder, mapping cone of the inclusion. So that means you have X, you have A. So the mapping cylinder we've talked about in class, this would be where you take a cylinder, A cross the interval, and then you attach it to X by identifying A with its image under the map. Of course, the map is just the inclusion, so you're just identifying A with A as a subset of X. The mapping cone is similar, except that you then collapse the top of the cylinder to a single point. Right. So obviously in this space, anything in A you can contract down to the point. Right. And so here, let's look at the reduced homology of X union the cone on A. OK, well, the cone on A is contractible. So that means if we were to look at this sequence for the pair of spaces where that's the big space and then the cone of A is the smaller space, then every time there's an HNA, you would get 0, right? Because it's contractible. So all of its reduced homology groups are 0. So if this is 0 and this is 0, then this map is an isomorphism, right? So in this case, that would say that this is the same as this relative to the cone.
Can you explain that one more time?
Sure. So the claim is that this comes from the long exact sequence of the pair. And the pair is X union the cone, comma, the cone. OK, so we have a pair of spaces. We get a long exact sequence. And A here would be the cone on A in this particular application, right? So that means that this one and this one, especially, let's go ahead and put tildes on things. Those are 0, right? So if you have a long exact sequence and you have every third group equal to 0, that means that the map between the other two groups has to be an isomorphism.
Why don't we have reduced homology?
Oh, because it's a pair, so reduced homology and homology of a pair are the same. But yeah, we could go ahead and put reduced. OK, so now what we can do is excision. So excision says we're allowed to remove anything we like inside the cone as long as its closure is contained in the interior of the cone, right? So let's remove the cone tip, right? The cone tip is going to be Z. Right, so by excision, this is the same as this with X union the cone minus the cone tip and CA minus the cone tip, right? So let's label the cone tip as P. OK? But if you think about the cone, if you remove the cone tip, then homotopically that's the same as a cylinder, right? And you can just push the cylinder down. Right? So this deformation retract, let's just say homotopy equivalence to the pair X A. With tilde if we like. Okay. Okay, so then it's always true that the relative homology groups are geometric homology groups. You just have to kill A somehow, right? So if it's a good pair, you can collapse it. And in any case, you can always just cone it off. Okay. Okay, wonderful. So by doing this, we've paid off one of our debts, because previously we had computed the homologies of spheres, but using the long exact sequence where you collapse spaces, right? So now that's fully justified. So another thing that we anticipated is our next goal. We're going to show that if X has a delta complex structure, then the homology groups that you compute using the delta complex structure are the same as the homology groups that you get from the singular chains. Okay, and this is how we're going to prove that, in particular, it doesn't depend on which delta complex structure you use. Okay, so en route to this, let's figure out what Hn. Okay, let's look at this group. So on the one hand, we know exactly what this is, right? Because this is a good pair.
Is that supposed to be subscript?
It is. Thank you. Yes. Next semester, it'll be superscripts. Yeah. Yeah. Okay. So yes, we know how to compute this because this is a good pair. And so you can just take this and collapse a boundary. And if you do, you get Sn. Right? You get just a sphere, n-dimensional sphere. And we know that the nth cohomology group of the n-dimensional sphere is the integers. But what's going to be useful is to have a representative for a generator. Right? So the statement here is that this is generated by the identity map. Which I'll denote I sub n. Okay. So this is a singular n simplex, and so it defines a class in here, and the claim is that that class generates. Okay, so we'll prove this by induction. Okay, so there's nothing to do for n equal to 0. So assume it's true for n. Yeah, so let lambda, lambda be delta n minus the last face. So remember, all of the faces are given by removing a vertex, right? So by the last face, I mean remove the last vertex. That gives you a face. Remove that face, right? So the picture is meant to look like what you would get for the triangle, right? Okay, so look at the triple, long exact sequence. So delta n plus 1, its boundary, and then lambda. So plus 1, okay. Okay. So let's stare at this. Okay, this, so this guy is contractible, right? It's just like a disk. And this is part of its boundary. So you can just deformation retract this onto that, right? Just in the case of the triangle, you can just picture taking this side and pushing it up until you've retracted onto the other two sides. Right? In general, you would do the same thing. Just take the base and keep going up until you reach a boundary and stay there. Right? So this and this are the same up to homotopy. And relative homology, when you put a space and then itself, is always 0. Right? So this group is 0. Which makes this an isomorphism. Right? This one was 0 just by dimensional reasons.
Hn of boundary delta n plus 1, comma what?
On the last line.
Oh, sorry. That should,
Lambda.
yeah, should be like. Okay, so next, let's stare at this last one. So it was Hn boundary n plus 1 lambda. Okay, so let's think again about the triangle. So if we were looking at the triangle, the boundary would look like this, and now we're collapsing this part. Right? So all that's left here is that last face, and you're collapsing, well, you're collapsing the other side, so who cares? But in terms of this last face, you're collapsing all of its boundary. Right? So what you get here is the same as delta n collapse its boundary.
When you're writing lambda, you have delta n comma last face. So for a triangle, wouldn't that just be like you have the triangle and then you get rid of this part, so you still have everything inside?
Sorry, you're asking why is that other one 0?
I'm asking, like, can you draw a picture of lambda for the triangle?
Lambda is the picture of lambda for the triangle.
Okay.
So
Wouldn't it be the boundary of delta n minus the last face?
The boundary of delta. So are you saying for this group?
I think, are you just asking about what the definition of lambda is?
Yeah.
Yeah, I was wondering that.
Because for the triangle,
Uh-huh.
delta n includes everything inside the triangle. So when you just remove the last face, you would have like a shaded in lambda with the dotted line along the bottom.
So you're asking why is that group 0? That was so. okay, so for the triangle, I have the triangle, and it's all like this, right? And then I have the boundary of the triangle, and then I have lambda, right?
So
That's
for
it.
definition, lambda's not filled in.
Lambda is not filled in.
So then it should be boundary delta n rather than delta n.
Where?
In the definition of lambda.
Oh, okay. Thank you. Okay, thank you very much.
Also, are we, we're looking at this triple with the, with the long exact sequence.
Uh-huh.
And so we've got delta n plus 1, boundary of delta n plus 1, and then lambda is defined with delta n?
So, right, thanks. So let's put an n, and then this would be n plus 1.
Okay.
Yeah, so it's the lambda for this.
That's... makes a lot more sense then.
Okay, thank you. Okay. Great, so we know inductively this is generated by the identity map. So we just have to see what happens to, what does boundary do to the identity map. So boundary of I n plus 1 is going to be a sum, minus 1 to the k, of I n plus 1 restricted to the kth face. Right? But I want this boundary to map into this group. Right? So I want the class that this generates in here. Right? So what happens in here? Well, we're modding out by everything except for the last face. Right? So all of these faces don't matter until you get to the last one. Right? So in here, so let's say the equivalence class in here is equal to the last term. So it's plus or minus in. Right? Where I'm saying in plus 1 restricted to the last face is the identity map of that face up to a sign. I have a sign. Right? OK, so I know the boundary map, the connecting homomorphism, takes the identity map here to plus or minus the identity map here. But really all I care is that the connecting homomorphism is an isomorphism, and it takes this guy to a generator. Right? So that means that this must be a generator of the other group. Right? Yeah, or if you like, the equivalence class in this group.
Do you mean on the top line, hn plus 1, delta n plus 1, boundary delta n plus 1?
Here n plus 1.
And then
And
s1 to 2.
hn delta n. I think this is right because
Because over there you have n plus 1s.
so if I look at the boundary of delta n, that looks like a bunch of boundary of delta n plus 1. That looks like a bunch of delta n's. Right? And so when you look at this boundary and you mod out by that, all you're left is one of those faces modding out by its boundary.
Wait, so modding out by its boundary? So why wouldn't that be? Oh. Wait, why is it delta? Why is it n minus 1 there?
Oh, thank you.
Okay.
Thank you.
So does this only work when, I'm not even sure what I'm trying to ask. We're doing like h sub n, right? And
Yes.
like a whole bunch of different h sub things. And
Right.
we're also looking at the specific, like usually when we write out this long exact sequence, isn't it the same pair?
Uh-huh.
Here we're changing the spaces as we.
Right, it's because we have the long exact sequence of a triple. Right, when you have B inside A inside X, then you have pairs, but the pairs change.
Right, but it's still like x, a, and b, right?
That's right.
And then you would go down to hn minus 1 and hn minus 2, but you'd still be using like a, x, and b.
Absolutely. So this is what shows up in the long exact sequence of a triple, and we're just noticing that it's equal to this.
Okay.
Right.
That would be.
That would not
a
be in this.
different long exact
Exactly.
sequence.
Yes.
Okay.
Yes.
Can you say like even just a sentence about why the base case is trivial?
Sure. So H0 of a relative group would be 0, right? This would all be, yeah. So, right, this would be wrong for the 0th group, but the fact that it's generated by the identity map would be true. It would just be 0, and the class of the identity map would be 0.
So did we prove that the rest of them are isomorphic to the integers?
Right, we already know that they're isomorphic to the integers, right? Because
Okay,
this is
okay.
the same as the hn of Sn. Right.
Okay.
Right, so we already know that it's equal to the integers. We're just trying to give a generator. Okay. More questions on this? Yes?
I don't understand the boundary item plus 1. Why is that formula?
What, this thing on top?
No.
Oh, this. Oh, well, this is, so this is a singular n simplex, n plus 1 simplex, right? And so this is the formula for the boundary.
I mean, is that boundary the connecting homomorphism?
Right, so remember that the reason the connecting homomorphism is denoted by the boundary map is that when you're doing relative homology, the connecting homomorphism takes a class and just gives you, takes a relative class and just gives you its boundary, right? So in the long exact sequence of a pair, you take a relative class you represented by a relative cycle. So this is a cycle in X whose boundary is in A. And then the connecting homomorphism just takes the boundary, right? So that's why we have this confusing confluence of notation. This is for long exact sequence of a pair. Right. So that's why here we can compute the connecting homomorphism by just taking the boundary. Okay. Okay, more questions on this? Okay, excellent. So that's one fact we need for the proof of this equivalence. There's another fact we need. So suppose you have a family of spaces, and in each one you have a point such that this makes a good pair. Then if we make y equal to the space you get by taking the disjoint union and then identifying all of these points, and we have the inclusions, then the inclusions give us an isomorphism between the reduced homology groups and the reduced homology of Y.
What is singleton X of alpha here?
This is just a family of spaces. It's
Okay, okay.
a family of spaces.
Do you know what Y is?
Is that
How do I pronounce that?
This is the wedge. Well, no, it's the what is it called? Sorry.
Is it the join? Or
Join, but isn't join the star? Yeah. What do we call this one? Wedge sum. Yeah. Yeah. I don't know why I was getting confused, but sorry.
Is that where you connected by?
That's right. So it's where you identify. So it's defined for pointed spaces, right? So that's why we have points. We choose these points and then we just identify all of them together.
Okay, wait,
Anyways.
so I think, we probably learned it from more than, okay, wait, so this wedge along all of the alphas identifies all of those?
That's right.
Alphas together?
All of these points become a single point in Y.
Okay,
So like if each x alpha is a circle, we get a bouquet of circles.
Correct.
So when we say that each of those is a good pair,
Mm-hmm.
you mean with the set containing x alpha?
Yeah.
Okay.
Yeah. So these points have a neighborhood the deformation retracts down onto them.
direct sum, not direct product?
Direct sum, not direct product. Okay, and so the proof is pretty easy. Let's consider the pair XA to be the disjoint union of the X alphas with the disjoint union of the little x alphas. Okay, so then because we have a good pair, this is the same as the reduced homology of the quotient, which would be y.
wait, how do you know, I understand that each x alpha, little x alpha is a good pair, but how do you know that XA is a good pair?
Right, so take the neighborhood given by all of those neighborhoods you had, and then the deformation retract is just do the deformation in each space.
So your neighborhood is the union of all of the
Yeah.
neighborhoods? Okay.
So, sorry, when you say a disjoint union of x alpha with the capital X,
Yeah, take the disjoint union of these spaces.
oh yeah, it is just a disjoint union at that point.
Yeah.
You're saying take the union of all of them and don't attach the points.
That's right.
Okay, that makes sense then.
Okay. On the other hand, we saw one of the first things we saw for singular homology is that if you have a disjoint union of spaces, then you get the direct sum of the homologies. But these are individually good pairs. X alpha. No, I didn't need to say good pairs. This is just, we proved that the relative homology of a space with respect to a point is equal to the reduced homology. Right? That was one of the things we did right after we had long exact sequences. We said, well, since the reduced homology of a point is always 0, then the long exact sequence of a pair, when you compare a space with a point in that space, is just going to give you the reduced homology. Right? So that's also an isomorphism.
So essentially what this is saying is, earlier I think we had a result where if you just take a disjoint union, then that gives you the direct sum of the homology.
Mm-hmm.
And then here what this is saying is the equivalent for reduced homology is the wedge sum, gives you the direct sum.
Well, I mean, you could also take the disjoint union for reduced homology and get the direct sum.
Would you though? Because if you're taking a disjoint union, wouldn't you get an issue in the which one?
Zeroth.
Yeah.
Yeah,
zeroth.
so okay, fair enough. Up to the zeroth. Yeah.
Okay.
Mm-hmm. Okay, perfect. So those are the two lemmas we need for proving this result. Now we just need some more algebraic machinery. So algebraic machinery. The 5 lemma. Okay, so this is great. So let's say that you have A, B, C, D, E. Let's give ourselves some groups. And then A prime, B prime, C prime, E prime, I, J, K, L, I prime, J prime, K prime, L prime, and then maps between them. Alpha, beta, gamma, delta, epsilon. Okay, and assume the rows are exact. Okay, so part 1 would be if beta and delta are surjective, so I think for this one I need a condition on epsilon. Yeah, epsilon injective. Then gamma is surjective. And 2, if beta and delta are injective and alpha surjective, then gamma is injective. Okay, so you have 2 exact rows and maps between them. We want to conclude things about gamma. So whatever you want to conclude, injective or surjective, you need beta and delta to have that same property. And then you need one of the outside ones to have the opposite property. Right? So to prove surjectivity, we need this one to be injective. And to prove injectivity, we need this one to be surjective.
Is there any geometric reason for that?
Not that I can think of.
Okay, so it's just true.
There's a good algebraic reason for it, right? Which we'll see in a moment. Yeah, the way this is often used, which is why it's called the 5 lemma, is if alpha, beta, delta, and epsilon are isomorphisms, then gamma is an isomorphism. So most of the time when you apply this, you have 2 long exact sequences, and you have maps between them. And so then if you know that 4 out of every 5 are isomorphisms, then the 5th one is an isomorphism too. Okay? So this gets used all the time. inductive arguments. Okay, wonderful. So let's prove these. The proof is diagram chasing. So it's great, especially if you have this. If you have the hypotheses given to you like minimally like this, then it's really easy because you know exactly what you have to use. So there's no choice, right? Okay, so we want to prove that gamma is surjective. So I want to show. Gamma surjective. Okay, so pick somebody here. We want to show it's surjective. Okay. Well, if you have somebody here in this diagram, there's nothing you can do except hit it with K prime. Right? Okay, so let okay, we have K prime of C prime gives us an element of D prime. Okay, now we know delta is surjective, so we can lift that guy up. Yes?
I'm assuming this diagram computes.
Yes, sorry. Otherwise, there's nothing you can do. Yeah.
Otherwise, what's the point of the entire lower half of the diagram?
That's right. Okay, perfect. So we start here, so we can move this way, and now we use that this is surjective to go up. All right? Since delta is surjective, there exists D in D such that delta of D is equal to K prime of C prime. Okay? Now, of course, here we also could have gone to the right, but since this is exact, we would have just gotten 0. Right? Okay, but so what's that tell us about the place we're at here? Well, if you went down and to the right, you would get 0. So that means that if you go right and down, you also get 0. Right? So, you know, epsilon of L of D is equal to L prime of delta of D, which is L prime of K prime of C prime, and so 0. Okay, but epsilon is injective. So if epsilon of this is equal to 0, then L of D is equal to 0. Okay, so we have an element here, and we've shown that if you go to the right, you get 0. Right? Because the top row is exact, if it's in the kernel of L, it must be in the image of K. Okay, so that means there exists C and Z such that K of C is equal to D. Okay. Wonderful. So we started with an element here, and we've worked our way up to here. Right? So of course, we hit it with gamma, and we try to see if we've won. Right? So let's compare C minus gamma, C prime minus gamma of C. Right? So what can we do? We can hit this with K prime. Okay, so K prime of C prime was, oh, we didn't give it a name, so it's K prime of C prime. minus k prime of gamma of c. But k prime of gamma of c, because this commutes, is the same as delta of k of c. Delta of k of c, but that's delta of d. And delta of d is k prime of c prime. OK, so I don't know if this is 0, but I know that if I hit it with k prime, I get 0. Right? So that means it comes from somebody in b prime. Right? So such that j prime of b prime is equal to this difference. OK. OK, so we're almost done. We've got something in b prime, and we know that beta is surjective. So we can take that and lift it up to here. Right? OK, so there exists b in b such that beta b is equal to b prime. OK. OK, so we have somebody over here. We want to know what happens if you go this way and this way. Well, it's the same as going this way and this way, right? So if you do gamma of j of b, that's the same as doing j prime of beta of b. So that's j prime of b prime, and j prime of b prime is equal to c minus c prime minus gamma of c. OK? So gamma of something is equal to c prime minus gamma of something. So gamma of c plus j of b is equal to c prime. Right? And we've won. Because we wanted to show that gamma was surjective, we started with an arbitrary c prime, and it's in the image of gamma. OK, let's prove this other one. OK, so for 2, we want to show that gamma is injective. And so we know that beta and delta are injective and alpha is surjective. Okay? So it's a homomorphism. We want to show it's injective. We just need to show that if you're in the kernel, you're 0. Right? So let C in C be such that gamma of C is equal to 0. OK, so again, you just have to follow your nose. We're in C. If we go down, we get 0. So the only thing we can do is go to the right. Right? And we know that if you were to go here and here, it would be the same as going here and here. And since you got 0 going down, you get 0 going here. So it must be that this gives us 0. Right? So what we know is that delta of k of c is the same as k prime of gamma of c is equal to 0. Right? And we know that delta is injective. So that means k of c must be 0. Right? Okay, but if k of c is 0, then exactness of the top row tells you that you were actually in the image of j. Okay. Okay, great. So we have somebody here, and we know we get C when we go this way, right? So what we know about C is that if you go down, you get 0. So we're here. We know that if we go like that, we get 0. So it must be that if we go like that, we get 0. So J prime of beta of B is equal to gamma of J. This is 0. J prime of beta. Right, that's what we got. Okay. So great. So what this tells us is you have this guy beta of B, and so we're here, and if we go to the right, we get 0. So that means it comes from somebody on the left. So by exactness, there exists A prime such that I prime of A prime is equal to beta of B. Okay, and we know that alpha is surjective, right? So we've made it A prime, then we can use surjectivity of alpha to lift to A, right? Alpha surjective. And alpha for A is A prime. Okay, so we know what happens. We're up here. We know what happens if we go like this. So that means we know what happens if we go like that. Right? So beta of I of A is equal to alpha I prime of alpha of A. So that's I prime of A prime, and I prime of A prime is equal to beta of B. Okay, but beta is injective. So we know that B is equal to I of A, right? But we know that J of B is equal to C. So C, J of B, J of I of A, right? But the top row is exact. And so if you compose two arrows, you get 0. Okay. So that gives us the 5 lemma. Sometimes parts 1 and 2 are called the 4 lemmas, because you only need 4 of the groups, right? But anyway.
No lemmas for other numbers?
No.
No. Okay, so yeah, I think we're all set. So let X be a space with a delta complex structure. There is an inclusion right, is it there? The inclusion of chain complexes. So for X, we have the delta complex structure groups, right? So these were the finite free abelian groups on the n simplices of the delta complex structure. And that maps into the singular chains of X, right? Because here you have all possible maps from the standard n simplex into X. Right? So this is an inclusion of chain complexes. It is a map of complexes. This commutes with the boundary because the boundary was defined the same way in both cases. So it induces a map in cohomology, in homology, induces an isomorphism. Okay, so the proof splits into two parts, depending on whether or not X is finite dimensional, right? Because you could have a delta complex structure where you just keep adding cells of all dimensions, right? So first assume that, and really what I want is the delta complex structure of X is finite dimensional. Right, so you only involve simplices up to some dimension. Okay, so let's do this by induction. Induction on the maximum dimension of the simplices in the delta complex structure. Right? So if, call it k, if k is equal to 0, then we just have points. Right? Then hk delta of x is the same. X is points. Right, and that's because we've already seen that for disjoint union, the for disjoint union spaces, this splits up into the disjoint union, the direct sum of the homology groups, and the homology group of each point is just said in degree 0, right? Whereas this one, the whole complex would just have a group in 0th place, and it would be the direct sum of seds, one sed per point, because there's only one possible delta complex structure on a point. So assume true for k. Right, let's recall XL is the L skeleton of X. So this is the structure, this is the space you get by only looking at the delta complex structure up to L simplices. Right? So we talked about this in the more general context of a cell complex. Okay, so do we want the pair? Yeah, so. And consider the pair. Okay, so we get a long exact sequence in each homology. So I mentioned this when we were talking about excision. The simplicial homology also has long exact sequences for pairs. You just need the subspace A to be not just a subspace, it needs to have a delta complex structure, and that delta complex structure should be a substructure of the one for x, right? But as soon as you have that, which we do here, then you get long exact sequences in simplicial homology by the same mechanism as you do for singular homology. Namely, the short exact sequence of complexes gives you a long exact sequence. So I want to put that one on top. So. Okay.
I hate to say this, but if we're going to be using the 5 lemma, shouldn't we probably put one more?
We could, sure.
I hate to say it.
Uh-huh. N minus 1, xk. Okay, there you go. Okay. Great. So now induction tells us that these are isomorphisms. Right, so this is by induction. Okay, so we need to stare at this arrow and this arrow and see that they're isomorphisms. Right? Okay, so fortunately we have those lemmas we proved beforehand. So let's see, delta n of xk plus 1 xk. This is 0 if n is not equal to k, and otherwise it's the free abelian group on the k simplices, the k plus 1 simplices. So, and right, because we know what these guys are. It's just a free abelian group on the simplices in the delta complex structure. So if you're looking at up to k plus 1 and you kill everybody up to degree k, then you're just left with the ones at degree k plus 1. Right? So if that's what the complex looks like, then the same is true for the simplicial homology. Right? It's also going to vanish if n is different from k plus 1, and here it's just going to be the same free abelian group. All right, so the ones on top are easy to compute. Okay, for the ones on the bottom, let's let phi from the disjoint union, say over alpha, delta k alpha boundary. Oh, k plus 1. So let these be the characteristic maps of the delta complex structure. Right? So this induces a homeomorphism of quotient spaces so it induces an isomorphism of singular homology groups so we get that the relative homology, singular homology is also equal to 0 if n is not k plus 1, and it's the free abelian group on relative cycles given by the characteristic maps if of k plus 1 cells if n is equal to k plus 1. Right, and so why are these generators? That's because we proved that h and k plus 1 of delta k plus 1 delta k is generated by the identity map.
Let's say relative cycles?
Yes.
By characteristic maps?
Relative cycles given by characteristic maps of k plus 1 cells. All right, so this is what the lemmas we proved before buys us, that we know what this singular homology group is, and we know what the generators are. And that's great. So this map, so we have the inclusion of chain complexes, and these generators include to these generators. So these maps are isomorphisms. Right? So all right over there. So this is an isomorphism for every n. Then by the 5 lemma, it gives us the inductive step. Okay, because once we know that this is always an isomorphism, then this is an isomorphism, and this is an isomorphism. And so by the 5 lemma, this is an isomorphism. Right. Okay, of course, that's only if X is finite dimensional. Right, so we have to worry of what happens if you have a delta complex structure with cells of arbitrary dimension. Okay, so if the if the delta complex structure on X has cells of arbitrary large. Okay, so in this case, you reduce to the finite dimensional case using compactness. The standard n simplex, the standard n simplex is compact. So its image is going to be compact, right? And so here's a key fact. Well, let's call it a claim because I'll prove it. If K is a compact set, and only finitely many simplices in the delta complex structure satisfy that if you look at what happens to the interior, it intersects X. Right. So when you look at the simplices in the delta complex structure, right, then only finitely many of their interior images can intersect this K. Because it's compact, yeah. So, yeah, the point is that if let's say delta sigma sub alpha delta n x do this, well, have sigma alpha x alpha in K for some x alpha in delta n, then you construct a cover u alpha equal to x minus union beta alpha of right. So all we're going to do is pick points that get mapped into K from the interior, and take the inverse of these guys, right? So these open sets have the property that this one has x alpha, the point, well, sigma alpha of x alpha, and nobody else does. So how do I know nobody else does? Remember that in the delta complex structure, the every point is in the interior image of a single simplex. Right? There's a unique simplex, singular simplex in the delta complex structure that maps. So I know that sigma alpha x alpha is in u alpha and not in u beta for beta different from alpha. And compactness of K gives a finite subcover. Right, so that proves the claim. Okay. Okay, so now we use this fact together with the case we've already proven to prove that we have an isomorphism in general. Right? So let's show that hn delta of x to hn of X is surjective. Okay, well, given a class in here, no, let's say, I don't really care. This you represent it by a singular n simplex, right? And then the image of this guy is a compact subset. Right? So since it's compact, it only meets finitely many simplices of the delta complex structure. So sigma is the class of sigma is actually in Hn of xk for some k. Right, and we know that Hn delta of xk is isomorphic to Hn of xk. So in particular, there's a class here that maps onto that class. A class. Okay. Perfect. So similarly, this is injective. Right. So if we have so for this to fail to be injective, you have some class in here, and when you map it over here, it's a boundary, and you want to know that you started out with a boundary, right? So let's say you have a class in here such that this representative C is a boundary of some B for some B in C n plus 1 of X. So this B is a map from delta n plus 1 to X. Only B of delta n plus 1, and this is compact. Right. So again, this B is a chain that only meets finitely many of the simplices from the delta complex structure of X, and so so injectivity of Hn delta xk to Hn xk for every k implies injectivity. Okay. And we'll stop there.